I want to take a little bit here and explain my favorite thing that I got out of calculus. This is a proof for the formula that we commonly memorize for volume, and for some reason I really like it. I find it absolutely fascinating and beautiful. What color do I want to use? Let's use green. So the formula as memorized is volume equals 4/3 pi r cubed. And in order to arrive at this formula, normally it's just memorized like in high school, but say you didn't know what it was, you can find it. And we're going to have to start by reviewing the formula for area. Area equals pi, it's supposed to be a pi r squared. Okay, and then what we're going to do is we're going to use a method for finding volume using an integral. And so normally you would look at just your 2D plane. I like the 3D plane here, so I'm going to try to work mostly on that. And kind of basically it says volume equals the integral from A to B, it's supposed to be a B, of whatever your area of your slice is, which I'll explain in a minute, dx. This can be set up in many different ways actually, but for our purposes this is the like the shell that we're going to use. So if I take my sphere here and I draw an axis here and I draw an axis here and an axis here, I'll pretend it's straight. So put my little arrows. Okay, so we will label this axis y. It's going to be a little more visually match the 2D version, which is what all you technically need. And then this is z. So we have our x-axis, y-axis, and our z-axis. And if we go back to kind of 2D world, so let's say this represents the same sphere. If we're just looking at just the x and the y-axis, ignoring the z. Oh, I labeled, oops. Get rid of that, that's not z. This is z. Sorry about that. So the z-axis would be what extends towards the camera in this 2D world. So we have our y-axis, our x-axis, and something that looks sort of like a circle here. Yeah, it's really hard to draw with a mouse. So that's our circle, which is why we're using the ready-made graphic here. But what we have for our circle, the area of a circle equals pi r squared, and this big circle here represents the sphere. Okay, but if we took like say a blade, let's get back to pink. So if we took a blade and we held it over top of our sphere here, can't draw up there, pretend that's like a razor blade or something, and we moved it downward parallel to the y-axis and perpendicular to the x-axis, and we cut, I'll draw like say we came straight down and we sliced a straight line right down here, right? Oops. And so probably we would first hit right about here, we would last hit maybe right about here, and then the shape that it would form, our little slice, would be a circle shape, which try to draw. Okay, so imagine that's a circle. And if we go back to the 2D view, I drew it on the left-hand side, so we'll do that over here too. It would be like a circle like that. This extends out into 3D space. And so going back to our sphere here, what we need to know is this position all the way at the left edge, and this position all the way at the right edge. That is where the sphere first touches the x-axis on the left, and then last touches the x-axis on the right. And what these are going to be is negative r. For now, I'll do sub s. Eventually, I'm going to get rid of that, but so this is the radius of the sphere on the negative x value of the radius of the sphere, right? So from the origin to the edge, to the radius, the length, the radius from the origin to the outer edge on the x-axis. And then this number over here will be positive r sub s. That's the x value at this point. So whatever this point is, where the outer circumference of the sphere touches this point on the x-axis, that point in our 3D space would have x, y, and z coordinates. But the only one we're concerned about right now is the x coordinate. And the x coordinate would be negative r sub s. And the x coordinate over here would be positive r sub s. So that's what we're going to use for A and B. So over here we're going to say, I'm going to start to fill in some of those. So volume equals the integral from negative r to r, and the area, so the area of this circle, which is supposed to look like a circle, is going to be pi r squared. The r for this circle is not the same as the r for the radius of the sphere. There's actually one place where the radius of the sphere will be the same as the radius of circle, and that's if my circle, as I'm moving along this axis here, if my circle crosses exactly on the y-axis. So if it's dead center at the y-axis, now my radius from my origin to my outer point of my sphere, that radius equals the whole radius of the sphere. But any other point, it's going to be smaller, all the way down to the outside edges. The radius of the circle would be 0. So back to my formula over here, generic formula, volume equals integral from a to b of a dx. So for a, we're going to plug in the area of the slice that we're making. And the slice is a circle, so the area is pi r squared. Let me go back to, I should have put sub s here. The reason is because this is going to be pi r sub c squared dx stays. So this r sub c is the radius of the circle, the 2D circle. R sub s is the radius of the 3D sphere. Okay, and the reason that this formula works is, so kind of a little quick explanation of what an integral is. This won't really teach you how to do integrals, but you know, if you don't already know what an integral is, so an integral is a sum. Okay, so we're summing all of the slices from negative r sub s to positive r sub s. So what this says is, as we move along the x-axis, traveling from negative r sub s to positive r sub s, again, from negative r sub s to positive r sub s, then we're going to sum together whatever we have right here, and the dx kind of says we're moving along the x-axis. So what we have here is the area of a circle. So what we're saying is if we add up the areas of every little circle that we can make from here to here, the sum of all those areas will equal our volume, which is a little bit intuitive actually. And so let me just use a color real quick here. If we made a slice over here and made a circle, if we made a slice here and made a circle, except these have to be right next to each other, but I can't draw that obviously. If we make a slice right here, a slice right here, and so on. Oh, that's a terrible slice. You know, all the way through the circle, and we add up every one of those slices, that's going to give us the volume. Okay? Now, in order to, so we kind of have what we need right here. This is actually what we're going to try to solve. But in order to solve this, we want to get this r sub c to have the variable x instead of this variable r. And about these variables, r sub s in this is kind of a constant. Just for right now, imagine that this is a specific circle. So really we could measure r, the rate, we could measure r sub s, and r sub s doesn't change. As we're doing this integration, as we're moving from negative r sub s to positive r sub s, the radius of the sphere does not change. So these are kind of like constants. R sub c is a variable in that as we move from negative r sub s to positive r sub s, as we travel along that x-axis, r sub c, the radius of the circle, does change because the circle size changes. When you're here, you're going to have a really small circle. This will be like a medium-sized circle. This will be the biggest circle. This will be a medium-sized circle, and this will be a very small circle. Okay. So what can we do? How can we figure out the radius of that circle in terms of x? Let me get out maybe some yellow here. Yeah, I like yellow. So this, oh, yellow's kind of hard to see actually. Let's try blue. Yeah, this represents the radius of our circle. So this is supposed to be the center of my circle. Kind of got to use your imagination. My drawing's not very good. This is the center of my circle. This is my circle, and it's perpendicular to the x-axis. It's parallel to the y-axis. So this right here represents r sub c. This, sorry, oops. That actually doesn't represent r sub c. This one, the hypotenuse of the right triangle that I'm starting to form here. That's a right triangle. This right here represents the radius of the sphere. So r sub c. Unfortunately, that's a little hard to see there as well. So now this is r sub c no matter where you create the slice. And once again, I'll do some yellow. You can kind of see that. So if let me try to draw my center point first. If I make this, it almost looks like a circle. Yeah, that's absolutely terrible. It would be smaller anyway. So let's say that, okay? If my circle is right here, my actually this is nice because they have this really thin green line here, which I can retrace real quick. So this thin green line represents, like, if you were to put a mohawk on this exactly center along that. So this is what do I want to say? This is like always in line with the x-axis as you move along here. In relation to z now is what I'm considering. It's not negative z this way. It's not positive z this way. It's always like z0 as you move along here. And this is always going to be the top of my little circle. So this circle should actually be up here. And anywhere I put my circle, my distance from the origin to the tippy top of my circle that I'm drawing will always be r. So if I were to go from the origin to up here and have a circle that big, you see that the hypotenuse of this right triangle that I'm drawing is always r. Maybe if I put one over here, you'll see that the x value changes, the y value changes, but this is always r. The hypotenuse is always r. Get rid of all that yellow. One more. So that's how our little right triangle is going to help us, because we see r sub c in there. Actually, sorry, my mistake. This is r sub s, which I just clearly explained. This is the radius of the sphere. This actually is r sub c. I don't usually use the subscripts, that's why I'm kind of getting confused. This is r sub c, so this is the radius of the circle. The radius of the circle, the circle slice, does change. The radius of the sphere, which I just demonstrated, does not change. But radius of the circle equals y. Okay, so the distance from the origin of my circle, not the, it's already blue, let's do yellow again, not the origin of my sphere, but the origin of my circle to the outer point of my circle, that's still keeping us at z0. Okay, we're only paying attention to z0 because we're imagining this 2D space right now. This height right here is a y value. It is equal to y of whatever equation I'm using to like draw this arc from here to here. Okay, so it would be the y value. And then this one along the bottom would be the x value. How far is it from here to here? Well, if this is my point that I'm kind of thinking about right now, right up here, this point, then this point is xy. Really hard to see that. This point is xy, and the length of the base is the x value, the height is the y value. Get rid of the yellow. A little more yellow. I think that's it. So, yeah, so this is x, and or this is y. This one down here is x. So now we can start to rewrite this a little bit. We could skip a step, but because I already went over the next step, but we'll kind of do them in order. So we could say now that volume equals the integral from negative r sub s to r sub s. Oops, it's supposed to be a sub s. So bad. Pi. And now we can substitute in y, which I just shown. Y squared dx. So we can substitute in y, which is helpful. However, it is not what we need because we want an x variable there. It will make integration work out nicely. So let's clear up some space. There's a way to do this. Change this to brown. Let's get rid of all this right here. There. Okay, so now we have some new space. Oops. Pencil. Green. Okay, so what do we know about y? Can we get y in terms of x? Well, due to the Pythagorean theorem, we have these three lengths here, the two bases and the hypotenuse. I think that would be right. The base height and hypotenuse. Anyway, whatever. So we know that y squared plus x squared equals r sub c squared. And that's because a squared plus b squared equals c squared. So, well, I switched the letters, but x squared plus y squared equals r sub s squared. And so right now we want to solve for y because we're trying to get rid of that y. So if you work this out, you'll see that y equals the square root of r sub c squared minus x squared. Now we can plug this in to our equation right here, and this will be very helpful because we're going to have r sub c squared. Sorry, that's an s. There I go, mixing those up again. That's supposed to be r sub s. I saw that and I thought, r sub c is not going to work. It's because it's supposed to be r sub s, which I demonstrated earlier. There's the s right here that's really hard to see. So, green's a little better. This is r sub s squared. And as I mentioned earlier, r sub s is basically a constant for our purposes right now. And that means it will be okay for integration. It will still work out easily. And the x squared, well, x is the variable that we want. So this right here is good to go. Back to pink. So right now, if we substitute in, we have this equals integral from negative r sub s to positive r sub s. Again, that represents moving along this x-axis. We're going to be adding up all of the slices along this x-axis to find the volume. Pi times the square root of r sub s squared minus x squared squared dx. And now, I don't know what the quickest way to get rid of this is. Probably like this. No, that's not going to be fast. Let's do this number. There. Okay, now. So now we have this formula, and now all we have to do is solve it algebraically. This is volume equals actually, let me skip that. So I'm going to clean it up a little bit. So if we are finding, our goal is to find volume, right? And volume represents the sum of all of the little slices from negative r sub s as we travel along to r sub s. And we're going to add all those up. But we could actually start at the origin here. If we just started with the circle that's at the origin, and we travel along the x-axis and add those slices up, well, clearly that's going to be the volume of half of the sphere. And so what we can do is find the volume of half of the sphere and multiply it by 2. And that just ends up making the integral solvable with less steps. It just works out easier algebraically. So we're going to do that. And the other thing we're going to do is we can pull these constants outside of the integration symbol. So we're going to do that. So we're going to have 2, which we got because we're going to just, now we're going to do half of the sphere and just multiply that by 2. Pi, which we pulled we pulled this pi out. The integral, now we're not starting at negative r sub s, we're starting at 0. And then for this r sub s, we don't have any r sub c's anymore, so I don't have to use that. I'm just going to write r because writing the subscript all the time is annoying. So 2 pi times the integral from 0, which is 0, to r. Now this is the r, what I mean by r right there, of, and then this whole thing is under a square root sign. We're squaring it so we can get rid of that. So once again, r sub s, we're just going to call it r, just so it saves me, it makes it a little easier for me trying to write it on with my mouse. R squared minus x squared dx. And now you can actually solve this. You can take the integral. So quickly, 2 pi. This is technically a constant, so we're going to treat it as a constant. So we just need to multiply it by x. So xr squared minus x cubed over 3 going from 0 to r. Now, normally we would plug in r for the x, then subtract what we have when we plug in zeros for the x's. But when we plug in 0, this is the reason we did this, because this term goes to 0, this term goes to 0. This whole thing will be 0 multiplied by this equals 0. So we're going to be subtracting away 0, so we can actually ignore that. So we're going to have 2 pi times, when we plug in r for x, we're going to have r times r squared, which is r cubed, minus r cubed, because we're just plugging in r for x, over 3. And then when we're subtracting these, this is 1 over 1. We can change it to 3 over 3 to find our common denominator. 3 minus 1 is 2. So we're going to end up with 2 pi times 2r cubed over 3. Now when we multiply in, 2 times 2 is 4. And since my end goal is to make it look like the original equation, this would be, I could put everything on top, but then when I put everything on top, I'll end up with 4 times some stuff divided by 3. I can pull the 4 over 3 out, which is what I'm going to do. So 4 over 3 times pi, because writing it to the side is the same as writing it on top, because if we multiply this out, the pi will go on top. And then we're left with this r cubed. So that is how you could come up with the formula for finding the volume of a sphere. 4/3 pi r cubed.